Good afternoon, everyone. We're from Salesforce. I'm sure a lot of you guys heard about us. The Salesforce Tower just opened up a few weeks ago, and we have been doing pretty well for the last few years, including rated as one of the most innovative companies in the world and the best places to work for. We all know that AI now is everywhere. Spark Summit, in fact, just renamed to Spark plus AI, and all the products and services that we've been using, like music streaming, household appliances, and transportation, and of course, advertising has become more and more personal and intimate thanks to the advancement of AI. At Salesforce, the AI initiative is called Einstein and has become one of the top priorities for us to achieve our growth goals. We all know that everyone engages with online services in their own unique way. Well, some likes to browse promotional emails occasionally, some engages with social network campaigns, some prefer certain colors, many find video ads very annoying. Some of us have our brain somewhat trained to filter out ads altogether, even though they're right in front of our faces. These are all very important information that will be very good for the marketers to know so that they can design a more personalized experience and prevent waste at the same time. For example, let's consider this scenario. I'm a Salesforce marketer, and I just deploy one piece of advertising on the web. Later on, I have more budget, so there's another banner ad, and then we have a new design, and then before I know it, I have about 8 advertisements on the web, including a video ad. In order for me to analyze the combined effects of these different pieces of advertising, I need to analyze about 256 different combinations, which is not too bad. If I want to add more dimensions, for example, maybe considering the placement, the size, the channel, maybe time of the day, it's not unreasonable to end up with 20 of those touchpoint items. Then we have about more than 1 million of those combinations. In a real case, however, on average, people typically involve 140,000 of those touchpoint items, which ranges from personal attributes, people's attributes, the attributes of the website they're engaging, events like emails, push notifications, et cetera, et cetera. But in this case, I don't even know what's the total number of combinations of 140,000. Some say it's more than the atoms of the universe. Good afternoon, everyone, again. My name is Kexin. With me is my colleague, Wanderley. We are here to talk about how we solve this problem at very large scale with the help of Apache Spark. This solution powers one of our Einstein products called Einstein Journey Insight, where it does exactly the thing with helping marketers to understand how different combinations of those touchpoint items and attributes affects consumer journey. And it surfaces insights like people who does X, visits Y, with some trait Z, is often associated with certain actions like convert. All right. Enough motivational talk, let's dive into the technical details. Although the combinatorics, what I just described, sounds very scary, but if you think about it a little bit more carefully, it's actually not that bad. First of all, not all possible combinations exist in the data. Second, even if they do exist, we want them to have a significant presence in the data sets in order to perform the analysis and to make them useful. The problem of finding all these patterns that have existence, have significant presence, is called frequent pattern mining, often also called the mining association rules. To illustrate what a frequent pattern mining is, let's use the same scenario. Let's label these advertising A, B, C, D, and E. And say we have these 10 users that saw different combinations of these ads. We can find the number of users that saw one ad, and number of users saw combinations of the ads. We often call these the number of rows for a given combination, the support of the combination. In order to define whether they're frequent or not, typically people will define a minimum support threshold. Let's say the minimum support threshold is 4. And we can immediately say that anything that have a support below this threshold is not frequent. In this case, E is not frequent. A E with support 2 is not frequent. And also, depends on the number of items that involve for different patterns. We call patterns with 1 item L1 patterns, patterns with 2 items L2 patterns, short for length 1 and length 2, basically. One of the most important properties given such a definition is called the a priori principle. That is, all subpatterns of a frequent patterns are frequent. How does that help us? Remember, we have, in the previous example, we defined the minimum support to be 4. That means E with support 3 is not frequent. Using a priori principle without even counting the number of any combinations, we can immediately say that AE is not frequent. Similarly, if we define minimum support to be 6, neither D or E are frequent. So we can immediately say without counting of any of their support, nothing that contains E or D are frequent. Because if they are frequent, then E or D has to be frequent in this case, which is clearly not the case. This is a very simple yet very powerful observation that is actually used by many of the frequent pattern mining algorithms that are out there. And one of the most efficient one is called FP growth. What FP growth does is it first scans the data twice and builds a tree-like structure called the FP tree. The first scan, it builds a thing called the header table. The header table is basically L1 frequent patterns with a support. However, they need to have their support sorted in descending order. And then the second scan, it uses this header table to build a tree structure. And then what you'll notice is that all the branches in this tree has to have the same order as the header table. That means if you see A above C in the header table, you will not see C above A in any branches in the tree. Also, you can find all occurrences of different items by following the link from the header table. I'm not going to cover how we are going to build this FP tree, but I'm going to concentrate on how we are mining the tree. Also, basically, if you see this tree, it's more of a compact version of the original data set. It has some aggregations, and the number here associated with each node represents how many occurrences you can find in the data. For example, A8, B5, C3. This branch represents there are at least 3 users saw the ads A, B, C. Okay. To mine such a tree, it's actually on a high level, it's a recursive process. Given an FP tree conditioned on the set of items alpha, you test whether it's a single path or not. So first of all, given a freshly built tree, the alpha set is an empty set. So if it's a single path tree, all you need to do is just calculate the number of combinations in the path, union them with a conditional item alpha, and then return them as a result. If it does not contain a single path, then you do a process for each item in the header table. You add the union of alpha and I to the result, and then call this mining again with FP tree conditioned on alpha union I. I know this is still very confusing. Let me show you with an example. This is the FP tree that we've been using earlier. So it's not a single path FP tree, so we're doing a mining process for each items. Let's say the item that we're dealing with in this case is C. First of all, we need to add C union alpha to the FP frequent pattern results. In this case, alpha is empty set, so C union alpha, we immediately have the first result, the first frequent pattern, which is C with support 6. To build the FP tree condition on C, we need to find, all we need to do is looking at all the items above C in the FP tree. So in this case, and also find out the patterns that it represents. In this case, by looking at a shorter version of the tree, we have ABC with support 3, AC with support 1, and BC with support 2. And then we simply feed that data again to build the FP tree. And in this case, we have one single path, which is AB. And then now we're going to the yes path and generating all combinations. In this case, AB represents A, B, and AB, of course. And then union them with C. And then we'll have the results. So on the high level, I want you to get understanding is this is a recursive process that we have mining process done based on the header table entries. So FP growth is very good if you can afford to scan the data a couple of times using one single machine, and also have the FP tree fit into the main memory. However, in reality, it's not the case. At Salesforce DMP, which is a subcloud of Marketing Cloud, the data we're processing are enormous. There's no way we can perform scans over the data set, let alone fitting the tree into one single machine's memory. We have to use distributed computing frameworks like Spark. What Spark does is it partitions data into different splits, and then it processes things on their individual executors, and then union them at the end using some kind of reduce operations. However, in this case, it's pretty obvious that we cannot simply partition the data, because if we partition the data randomly and split them into different nodes, we have to build and mine them using very low support in order to making sure we're not losing any patterns. And the effect of having very low support is that there's not much pruning power there is, and building massive trees on their local nodes as well, so it's not going to work. However, there's no need to be discouraged by that. If you think about it more carefully, what makes the tree very large? There are two main factors here. One thing is number of items and a large number of rows. It turns out the FP growth algorithm can deal with either large number of items or large number of rows, but not both. If you have very large number of items, but not a lot of rows, the support pruning is actually very effective to reduce the tree size. On the other hand, if you have a lot of rows, but not that many items, it can aggregate. So all these branches will be aggregating, so in the result, you have very small trees as well. It's only when both of them are large, then we run into troubles. So recall how the mining process goes. We perform, when the tree is not a single path tree, we perform this mining process on each item in the header table. That means we mine based on the FP tree condition on A, B, C, D, E separately. And then in the end, they actually produce different subsets of the frequent pattern results. So this, instead of looking at the data, but at the mining process, it starts to look like something that we can perform pretty well on a distributed computing framework. So how does that work? And also, in addition, if you look at the thing, when we mine the conditional tree, when we build a conditional tree on C, we actually do not look at things that below C. So we only look at C and anything above it. This means that for each mining process, it actually returns the pattern that definitely contains the conditional item, maybe contains the items above the conditional item, but that definitely does not contain anything below it. This also making sure that all of those iterations is to actually return a non-overlapping subset of the results. So this give us something that we can work here, and all we need to do is to making sure that each node gets only the necessary data required for the mining process. In this case, all we need to do is finding the items above them. For this case, if we're mining the thing for a conditional item on C, all we need is U2, U3, U5, U6, U8, and U10. And also, in addition, U3 does not need BC, U6 does not need B because they're items below the header table. We can do the same for E, D, and B. And as it turns out, you can see that when each individual mining goes, it does only handle either large number of rows or large number of items, but never both. To write it is actually pretty simple. First of all, you just need to build the header table, distribute the rows based on the rules according to the header table, mine them separately. In the end, all you need to do is collect the patterns. Right? To implement it in Spark is also very trivial as well. The header table is basically counting the frequency, and distributing the data is the flat map followed by group by key, and then to apply minings for each individual node, it's another flat map away. And Spark handles all the data distribution and the mining process for us. I'll let my colleague Wanderley to continue this discussion.
Thank you, Kexin. Okay. So let's shift our conversation and talk about mu support. There are very few concepts in frequent pattern mining that are more important than minimal support. Finding the proper value of mu support is what will make our very hard combinatorics problem tractable so that we don't have to handle, quote, all the atoms of the universe. However, for such important role, we found very little guidance on how to set that value properly, other than by doing some trial and error. And by doing trial and error, we found that the process was particularly challenging. So let me show you what I mean by that through some examples. Here is a typical situation that you would expect to find when dealing with a typical marketer use case. The bars represent items, things like ad views or clicks, with their respective support levels. We want to mine these items for frequent patterns, so first we need to set a proper min support threshold. So initially we set this threshold level to be somewhat high, and no surprisingly it did not work well because we produced very few patterns. It did not work because we set the min support too high, so most of the items like B, C, D, E were completely filtered out from the end results. So what we do next, we lower the min support threshold, and now we start to see more patterns. However, when we did that, we noticed a particular oddity on the results. None of the patterns that we find in the results contain clicks. We find quite unusual to be talking about things like conversions and didn't see clicks as part of something very valuable. It turns out that our min support level was low, but it was not low enough to accommodate clicks. Clicks are very valuable items, but they are rare. Their support level is several orders of magnitudes comparatively to ad viewing. And it would make sense if you consider that typical values for click-through rates are numbers like 1%, 0.1%, or even less than that. So in order to accommodate clicks, we lowered this bar even lower. But now what starts to happen is that our job starts to take too long to process. Some of them will not even terminate. And when they did, they will have produced too many patterns, most of them useless and indistinguishable from noise. It was clear that we have set our min support too low, so low that it was not doing its proper job. So all this led us to try to say, wait a minute, we need to extend the theory, something's not working. So we come up with our own min support framework, and that we call differential min support, aka DMS. The idea underlying DMS is a simple one. Since we cannot find a unique min support threshold that would solve our problems, why don't we divide and conquer? So we take all the items, we classify those items into categories, we compute the mean support per category, and we run FP mining algorithm with multiple mean support. So back to our example, we were having problems trying to find a global mean support. To solve this problem, we divide and conquer. So we can now identify two categories based on the item support, a common items category and a rare items category. This is just a better view of the two categories, and then we can compute the mean support separately. Here what happens is that we actually, the task of trying to find the mean support was actually generated several sub-problems to find the mean support for each category. But the good news is that because of categorization, we don't need to worry about missing rare items like clicks. We just have to worry about the mean support generating the right amount of patterns, not too much, not too few, and most importantly, being able to ensure that the sub-problem is tractable. Right? So we also do have an algorithm to do that, so we don't have to do it manually, category by category. The algorithm will just look at we collect some statistical properties for each of the categories. We use those properties to evaluate whether that sub-problem will be tractable or not, to what extent, and we'll set the mean support threshold accordingly. So problems with high complexity, higher mean support. Problems with lower complexity, lower mean support. So now what we have multiple mean supports, and we know how to compute them. The next step is how do we use that to determine whether a pattern is frequent or not. In the case of the traditional mean support threshold, the answer is quite easy. A pattern is frequent if its support is greater than the mean support, which is a unique number. But in our case, we have a pattern with multiple items, each belong to different categories, each with a different mean support. It is not clear to us what we should be comparing the support with, and it is not clear to us whether doing that simple comparison would be good enough. So we come up with another solution to that problem, which is formalized in this mathematical expression. In plain English, what this means is that a pattern is frequent if two conditions are met. The first condition says that a pattern is frequent if the support is greater than the pattern mean support, and the pattern mean support is defined as the lowest category mean support if you consider all items in the pattern. But this is unnecessary but not sufficient. We also need to ensure the a priori principle. So if a pattern is frequent, all subsets of that pattern must also be frequent. I'm going to group an example to show how this comes into place. Here are three items with the categories that they ABC, with the categories they belong to, the common item category, the rare items, and with their respective mean support. On the right table, we have all the possible combinations for ABC, AB, AC, BC, ABC, with their respective support levels. We first start by computing the pattern mean support. So we look at the compositions of the categories that are in the pattern and look at the lowest one. For AB, we have only common items. The mean support is 100K. Everyone else, we have C. So the pattern with the lowest number, which is 1K. Then we can check the conditions, and we found out that our combinations will meet condition 1, with exception of AB, which has a support 80K less than mean support. But here we have an inconsistency. We are saying that a pattern ABC is frequent, but one of its subsets, AB, is not. We need then to correct this inconsistency by applying the a priori principle and then correct the entries on the table. So this diagram shows how we're going to integrate the DMS into our FP growth distributed. Yeah? It all starts by generating a function mapping categories to mean support, which is the flow color in gray up there. This map, this function, is passed as a parameter to the distributed FP growth, which will in turn broadcast that map to all the executors. Remember that each of those executors is processing a conditional FP growth tree and will generate conditional patterns. So this is where we use the map to apply, to enforce condition 1, the pattern means support. We cannot apply condition 2 until we know all the subsets for all patterns, and that will not happen until all the partial results are aggregated in the process colored in blue. This is where we enforce at this stage, we enforce the condition 2, the a priori principle. We get the final results and output them. How to implement that Spark? That's easy. Remember dispatch of code some slides ago. Let's start with that. To implement condition 1, we just write the means support category, pass that, broadcast it, and pass an argument for mind for patterns method inside the second flat map. And this is how we implement condition 2, the a priori principle, which is just a filter on the final result set. So we are reaching the end of the presentation. This is not the end of the story. We have several other initiatives that we did. I will just mention them briefly before we adjourn. So we did some contributions we did some work on doing some low-level optimizations on the code. We also did some work to generate result sets that are more compact by removing patterns that provide redundant information. We also did develop some scores and metrics to rank the result sets accordingly. And most important also, this last item was a little more, we also extended the FP mining so that it can be applied to items with feature sets, multidimensional items. This is a quite complex, a more complex algorithmic and computational undertaking, but one that provided a lot of value to our clients, because now not only they can figure out what combinations work best, but what about those combinations make them work best. This is actually, by the way, a very well received feature of our platform. Kexin, would you like to do the final?
So, as you see, there are a lot of problems that we covered a few, and there are a lot of problems we didn't cover in terms of addressing large-scale data mining problems. Luckily, with Spark, we can actually concentrate on more of the difficult part, where how do we doing the distribution, how the algorithm works with each other, with different nodes, how the data distribution works. But we have Spark to handle shipping the data to nodes, applying the functions, the fault tolerance, and etc. So that concludes our talk. And any questions?
Please just go reach our microphone. If you have any questions, we have about a couple minutes.
Hi, I have a question about the rule that you have on eliminating the patterns with multiple thresholds. When you had ABC, you eliminated it because AB was not frequent. That sort of seems counterintuitive to me. Like, suppose A and B were page views and C is a click. Then the fact that ABC is frequent, it's even more important than in the case that AB is not frequent than if AB was frequent. It seems like it's even more interesting because there are fewer page views, but the click pattern is frequent. So do you feel like you're losing some of maybe interesting patterns in this kind of, when you eliminate it this way?
So do you mean the
multiple means support? You're saying we are going to lose some. We are going to lose some. We are going to have more diversity. There is a little to say whether those patterns were more important or interesting or not is a little bit after the fact, right? You need to have introduce some criteria in order to generate patterns with certain amounts and with certain levels of diversity. For the particular problem that we are trying to solve, we need to get a little bit more of diversity because clicks were missing. It's much better for us to have patterns that shows the full size of activities, including the right items, rather than having a a lot of combinations of ads that were working, right? So I would say that there's also tuning that we can do on that as well, right? So I would say that you may lose some of those as well, but I think the trade-off that we are getting was much better for our use case, and for most of the use case we'll be facing.
I think the main thing is for consistency as well. Like C itself will actually be exposed as frequent. But AB, combined with AB, because AB is already everywhere, so adding AB or without AD doesn't actually make a difference because it's everywhere already. And that's why we're having a higher threshold for them. Like because we're setting these up, if they're higher, then they have to meet a higher bar. That's why the recursive definition is imposed. Hope that makes sense.
Okay, yep, thank you.
Thank you very much for the presentation.
Thank you.